Hello.
Hey, how's it going? Just
Good.
trying to find my PowerPoint. Not a big deal. All right, it's quantum mechanics. That's not it. Okay, let's go for another one. All right, this one should be it. Hey, how we doing, ladies and gentlemen? How many of you do I have in here tonight?
Good.
I know I got 4 of you in here. I'd actually like to do something different. And that's basically, have you all had VSEPR? Have you had that in your lecture yet?
Yes.
Brian, Victoria,
Yes.
Brian?
I don't think so.
VSEPR is where they, where you kind of like do the Lewis dot structures, and then you use that to determine what the shape of the molecule is.
We are starting doing that.
Starting
right?
it? Okay, good
Yeah.
enough. Good enough. No, that's fine. I'm sorry, I'm gonna have to take, because of that, I'm gonna have to take you through the major portion of it. Somebody needs to remind me before I get off tonight that I have to take you through the results. I know I normally do go through the results section with you, right? I absolutely need to do that because it's kind of funky the way he has it done, okay? So, all right, so we're gonna go and I'm gonna try and do, thank you. My coffee caddy just came in here. Okay. There are some rules we have to deal with when we're dealing with Lewis dot structures. From the molecular formula, write down the elements. All right. And when you write them down, generally speaking, you put the least electronegative in the center. There is a reason for that. And that has to do with formal charges that I will get into later. But where you're going to have a chemical formula, write down the elements, put the least electronegative in the center if you can. Add up all the valence electrons. You have to account for charges. That means if I have something like SO4 2-, I got to look. I look and find the sulfur has 6 valence electrons. I have 4 oxygens. Each one of those has 6. So 6 times 4 is 24. I have 32 so far. Then I have to account for these 2 minuses. The 2 minuses are 2 extra electrons that the sulfur or the oxygens don't have. So that's just 2 extra oxygens. I have to include those as well. So with SO4 2-, if I have a negative charge, I have to add that many electrons to the valence electrons. On the other hand, if I have something like NH4+, I have to subtract 1 electron away to make up for the positive charge. So with NH4+, the 1 nitrogen has 5 valence electrons. The 4 hydrogens each have 1, but it's a +1. So I have to subtract 1 away from it. 5 plus 4 is 9, minus the 1, I have 8 valence electrons. Are we good with this, ladies and gentlemen? We good with this so far? All making sense now, right? Okay, now, the next thing is, you've got the symbols of the elements on the piece of paper. You need to put two dots, two electrons between each of the elements. This signifies that they're bonded together. Then count up all the bonding electrons you have, subtract those from the valence electrons you have. Next, fill up all the terminal atoms with pairs of electrons. You want to get 8 electrons around each of the terminal atoms. So if they all have 2 for the one bond, you're going to be putting 6 around them. Count up all the lone pairs and subtract that number of electrons from the ones remaining. If you have any leftover electrons, they go on the center atom. If at that point the center atom does not have 8 electrons, take a lone pair from one of the terminal atoms and put it between that terminal atom and the center atom. What you've done is create multiple bonds. Then you go back and check. Do these seem like rules that you've seen before? Kind of, sort of? Veronica, Brian, Victoria,
Yeah.
show your faces.
Yes.
I want to see faces tonight. This is the horrible thing. Victoria, come on, show your face. This is the horrible thing about teachers going and taking courses that are taught by other teachers. They get tricks. And actually, I like seeing your faces. So we're going to have faces from now on. Is there anybody else that's out there? Madison, Mac, and Ramiro, please, I want to see your faces. Mac, Madison, come on. Now, bottom line, these rules I've just gone through, they don't seem, they're nothing that you haven't had before, right? Each of you have had this at some point or another, correct? Brian?
Yes.
Have you seen some facsimile of these rules?
Yeah.
Okay. Now, I'm going to throw an absolute monkey wrench into this. And that is, up to this point, you guys were dealing with something called the octet rule, right? All the atoms could not disobey the octet rule. They all had to have 8 electrons around them, right? You remember that? That's not true. That's not true any longer. Okay? Because have you all had quantum mechanics? Veronica, Brian?
Mm-mm. No.
All right. Do you remember having quantum mechanics in intro? Do you remember that the electrons got into suborbitals like 1s2, 2s2, 2p6, 3s2, 3p6?
Oh, yeah.
Then it went to 4s2, 3d. Remember that?
Yeah.
Okay. Well, those 3d electrons, those are still in the third shell. Because those are in the third shell, they're accessible. So if you look at your periodic table, and I need to check to make sure, everything from aluminum over to the right and down, everything there can incorporate the 3d electrons. So they can have more than 8 electrons. if we're dealing from boron over to neon, there's no d electrons. No d electrons, so therefore they cannot obliterate the octet rule. At that point, they are all going to be 8 electrons. So let's go through and let's do a normal one first. I have SO2. Sulfur's not as electronegative as oxygen. I'm putting it in the center. All right. Just 1 second. This is yours. All righty now. The next thing my rules tell me to do is put 2 electrons between, well, first of all, it tells me to count up all the electrons. By the way, do you all have a periodic table in front of you? Now, if you haven't marked the periodic table now, you probably should mark a periodic table so you know how many valence electrons are in each atom. Everything from hydrogen down has 1 valence electron. Beryllium down, 2 valence electrons. Boron down 3, carbon down 4, nitrogen down 5, oxygen down 6, fluorine down 7, and everything on that far right-hand table, with the exception of helium, has 8. From neon on down, has 8. Helium has only 2. So if you don't know that about the valence electrons, you do now. When we're talking valence electrons, we are only talking the S and the P electrons. And I know some of you are pulling back from intro, but that is what we are dealing with. D electrons are not valence electrons because the S is in a higher shell than the d electrons are. Is that making sense to you? So we're only counting first 2 columns and the last 6 for valence electrons. So if I'm dealing with SO2, the sulfur has 6, 1 atom for 6 valence electrons. The oxygen, there are 2 atoms, each of them has 6 for 12. I have a total of 18 valence electrons. Rule 4, I got to put 2 electrons between each of the elements. Those are my bonds. I started off with 18. I've just used up 4 of them. So I have 14 left. Subtract the bonding electrons from the original amount of valence electrons. I have 14. My next rule says I put all of the extra electrons around the terminal atoms. Oxygen has 2, it can accommodate 6 more. So I put them around the terminal oxygens in pairs. First lone pair, second lone pair, third lone pair, 4th, 5th, 6th lone pair. I've just used up 12 electrons. Did somebody have a question?
Yes. Where did you get the 4 that we're subtracting?
All right, Veronica, I have to have a bond. If I don't have a bond, then this oxygen is not associated with that sulfur, right?
Yeah.
So I have to put 2 electrons between the sulfur and the oxygen to make that chemical bond.
Oh, okay. So, okay.
I do it on the left, I do it on the right. There are 2 bonding electrons on the left, 2 on the right. That's where the 4 came from, okay?
Okay.
So now I've got 12 lone pair electrons around my terminal atoms. I had 14 left. How many does that give me? Come on, let's do this quickly so we're not here all night. I had 14 left. I just
2.
used up 12 more. Thank you. There are 2 left. My rule says if I have 2 left, they go on the center atom at that point. All right. Now, I'm looking at this very nice molecule, only there is something wrong with it. What is wrong with this particular molecule?
Pairs on the outside.
I'm sorry, what?
The lone pairs on the outside.
No, the lone pairs are good. Lone pairs, I got oxygen can have 8 electrons. It has 2 bonding and 6 lone pair electrons. This one has 8, and this one also has 2 bonding electrons and 6 lone pairs. They're fine.
Sulfur doesn't pass the octet rule.
Sulfur doesn't pass the octet rule. So my rule is, what I do is I take the electrons from a terminal, put it in between to make a double bond. So those are the rules as you knew them going through introduction. If you check it out, each one of those atoms has a 8 electrons. Now, there are circumstances that exist that make it impossible to maintain the octet rule. If I have BF3, okay, my boron has 3 valence, my fluorine has 3 times 7 or 21, so I have a total of 24 valence electrons. Correct?
Correct.
Okay. I make, by the way, everybody knows that if you have a line, that's the same thing as having 2 dots. We're good with that? Okay, so I put a line between each of my fluorines and the boron. I've used up 6 electrons. I have 18 left. Okay? My next rule says I fill the terminal atoms with electrons. That gives me 6 around this fluorine, 6 around this fluorine, 6 around this fluorine. I have used up all of my electrons, correct? Now, the original rules told you to do what? Yeah, I realize the terminal electrons aren't, the lone pairs are not on here, but you're just going to have to imagine them for right now. It's the best I can do to draw. What did the old rules tell you to do? Are there enough electrons around the boron?
No.
So what did the old rules tell you to do?
Take 2
Borrow.
of the lone pairs from the fluorine and make a bond.
So that's what you're supposed to do, right? This fluorine now has 2 lone pairs. The other 2 fluorines have 3, right? Am I right on that?
Yes.
Thank you. I know it doesn't look pretty, but you're going to have to deal with it, okay? And we're going to go down here and okay. I know it's not pretty, but that's the way it is. This fluorine has 2 lone pairs on it and a double bond. This one has a single bond and two or three lone pairs. And the bottom one has 2, 4, 6 and a single bond to it. This is what you would expect, right, ladies and gentlemen? Until we go into thinking about something called formal charge. Formal charge is the charge on the atom as it exists in the molecule. And the way we do formal charge is equal to the normal valence electrons minus the lone pair electrons plus the bonding electrons divided by 2. Have you all seen something like this before? All right, this is how we figure out the charges on the individual atoms. So if I'm going to do that, and I'm looking at that fluorine, fluorine has how many normal valence electrons, as if it's just an atom?
7.
7.
So it's 7 minus, okay. How many lone pair electrons are around this fluorine?
2.
4, 6, right? So I have 6 lone pair electrons plus how many bonding electrons?
1.
2.
2. Veronica, 2 electrons make a bond. 1 bond, 2 electrons.
Okay.
So what is the formal charge on this fluorine? What's the normal charge on it? Look what it is.
3.
3?
No, the math. The math.
7 minus 2, 7 minus 6 plus 1 is 3? That's
0.
what we're doing. Is 7 minus 6 plus 1. What's the formal charge?
0.
Thank you. Is there anybody that's not saying that? 6 plus 2 over 2 is 7. 7 minus 7 is 0, right? All right. Can everybody see that the electrons around this fluorine are the same as this one? This one has 1 bond and 3 lone pairs, so its charge is also going to be 0. So I have 0 for this one, 0 for this one. Let's look at the boron. My formal charge for my boron, normal valence electrons, 3 minus, I have no lone pairs around my boron, but I have how many bonding electrons? 2, 4, 6, 8. I got the formal charge is 3 minus 0 plus 4. The formal charge on this fluorine is no, I'm sorry, excuse me. Wrong. The formal charge on this boron is a 1 minus. Everybody see that? Boron, 3 valence electrons, no lone pairs, 8 bonding electrons divided by 2. So the charge on that boron is a -1. What about this fluorine? Guys, you can do this now yourselves. How many valence electrons does fluorine have?
7.
7.
Thank you. Minus, how many lone pairs?
4.
4.
Yeah.
Why is isn't it
Plus-
6?
Because
Yeah.
the 2 electrons that were here went down there to help make the double bond. Who's asking a question?
It was Madison.
Madison, are you seeing it, Madison?
I see. I was looking at the other fluorine.
Okay, it's this one is the one we're talking about now. This one and this one are 0. All right, how many bonding electrons does that fluorine have?
4.
So the charge on this fluorine is 7 minus 4 plus 2. It is a 1 plus. Okay. Now, somebody riddle me this, ladies and gentlemen. What is the most electronegative element?
Fluorine?
So is fluorine ever going to be a +1 charge when it is next to boron? Is that possible? Fluorine's not even a +1 charge when it's next to fluorine. It will never, ever be a +1 charge. Therefore, this structure cannot exist. It exists as this. And when we have done crystallography studies of BF3, we've determined that it is a trigonal planar molecule, and therefore the boron only has 6 electrons. It violates the octet rule. Are we good with that? Are we good? Do we kind of understand why the octet rule gets violated in this instance?
So is it because it cannot be a +1?
Fluorine cannot be a +1 when it's next to boron. If you put this double bond there, you force fluorine to have a positive charge. Fluorine will never have a positive charge. Not possible. That's a bigger transgression than not giving the boron the 8 electrons. Okay, Veronica? Is that kind of making a little more sense now?
Is there a list of elements that I guess violate the octet rule, or do you just kind of have to try it and just fail?
Well, let me put it to you this way. What's the next one down from boron? What's the next element down from boron?
Aluminum?
Okay, is aluminum ever going to be involved in covalent bonding? It's a metal, right? So no, it's not going to be involved. This is the only one that I know of. I'm not saying there aren't others out there. This is the only one that I'm aware of. Okay? Okay, so I'm going to get into that in a second. All right. I have another molecule out here. ICl5. Iodine. How many valence electrons?
7.
How many atoms of iodine?
1.
All right. So iodine's contribution is 7 valence electrons. Chlorine. How many valence electrons?
7.
How many atoms do I have?
5.
So how many total valence electrons?
35.
So my total valence electrons, adding the chlorine ones and the iodine, I have 35 and 7, or a total of 42, right? Right?
Right.
Yes.
Okay, now, if I was going to draw an atom of chlorine or iodine, just drawing it out. That's what I would have, would I not? 7 electrons around the chlorine or 7 electrons around the bromine or iodine, right?
Yes.
How many things can possibly bond?
3.
How many unpaired electrons does this have?
Ampere.
As
One.
one unpaired electron. So wherever you have one of these things, you're going to cap the chain of the molecule. That's one thing. I've got 5 things here. I got 5 things around the iodine. So I have to put 5 bonds around the iodine, right? If I'm going to make this molecule, I've got 5 things that I have to attach. Name some other way I can attach this so that I don't get 5 things around iodine. Anybody? So the first thing I'm going to do is I'm going to put the chlorines around my iodine. And each one of them has 2 electrons so that I have 5 bonds. I started off with 42. I just used up 10. I've got 32 left. I put them around the terminal chlorines. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30. I have now put electrons around 6 lone pair electrons around each one of these chlorines. I subtracted it away from the valence electrons I had left. I've got 2. Those 2 electrons have to go somewhere. Where they go is right on the iodine as a lone pair. So in fact, I have my iodine has 2, 4, 6, 8, 10. It has 12 electrons around it. Is this making a little bit of sense to you?
It's not a double bond, or
No. A double bond with Veronica, if I put a double bond in there, it would make it even worse because a double bond conserves electrons. I put in double bonds when I don't have enough electrons. I have too many electrons here. So I don't want double bonds. If I put double bonds in there, this is just going to mean I have more stockpile of electrons that I need to take care of. Talk to me, guys.
so you just put it crossed?
I'm just indicating that this iodine has a lot. I have to put this somewhere. I'm indicating by doing this that this lone pair is associated with that iodine.
Okay.
You can just draw 2 dots, right?
If you want to, yes.
Oh,
I hate dots though. I can't stand dots. Okay. Yes, the inert gases will react and make compounds. XeF4 exists. I've got my Xe. It's got 8 valence electrons. My 4 fluorines have 7 each for 28. I've got a total of 36 valence electrons. How are we going to draw this?
You're
What?
gonna
What goes
put
in the center?
XE.
XE, yeah.
XE, and I'm going to put the 4 fluorines around it, correct?
Yes.
With 2 electrons between them to make bonds. Sort of like that, correct?
Correct.
Yes.
So I had 36 valence electrons. How many do I have left?
28.
28. I had 36. I used up 2, 4, 6, 8 of them, making the 4 bonds. So 8 minus 36 is 28. Where do those electrons go?
First around the fluorine.
Around the fluorines. And I know, I'm sorry, you just have to imagine that the lines or the dots are there. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. I've used up 24 electrons, putting them around the terminals. I had 28 left. I just used 24. How many electrons do I have left?
4.
And those 4 are going to go around the center atom. So in this case, my xenon has 12 electrons around it. Is this kind of making a little bit of sense, guys?
Yes.
All right. Now, I am going to do something. I am going to not insert, I'm going to do a new slide. All right. All right. How many different ways can I make this molecule? How many different ways can I put the C, S, and O together? Can I put it with the 3 different ways? Tell me what they are.
The S in the middle, the C in the middle, or the O in the middle?
Okay. Absolutely. I can do, right? I can do right? Or I can do, what do we say? S in the middle. Right? All 3 of those are technically possible, right?
Right.
Okay, now, this is going to be a long exercise. So just bear with me because we're going to be doing formal charges. Let's consider the CSO. Oh, yes, this one. Okay. Valence electrons. How many does carbon have?
4.
Sulfur?
6.
Oxygen.
6.
So I have 16 valence electrons, correct?
Correct.
So if I'm doing this, I've got 12 left, right, guys? So I have to put them around the center atoms, correct?
Yes.
Correct.
Now you understand why it's so hard to draw these silly things. All right. I've now used up all my electrons. but carbon doesn't have enough. So what do I have to do?
Double bar.
Double bonds. I can steal these and put them in there. And I can steal these and put them in there. So I can make something that looks like this. And that's a legitimate Lewis dot structure, correct, ladies and gentlemen? Right?
Yes.
Does it have to be double bonds? Can I put a triple bond in there?
Yes.
Okay, I can do and I'm getting fancy on you guys. Ooh, look at that. Is that the only way I can make a triple bond?
No, you can do it on the other side.
If these are both S, then doing a triple bond on the other side would just be the same molecule. It's just flipping the molecule around. But since I have an S on one side and an O on the other, it's a totally different molecule. I can make it like this.
So when we put the double and the triple bonds, is it because we need, what is it that we're missing that it needs more?
Okay, if you didn't put the double or triple bonds, carbon would only have 4 electrons around it. Okay, Veronica? It's
Yeah.
not stable enough. It's not stable enough. You need to have 8 around it.
Does, okay, and so the middle one does always have to have 8?
All of them should have 8 if it's possible.
Okay.
All right, if it's not possible, it's not possible. If for some other reason, like the fact that fluorine precludes you having a positive charge on it, then that's part of the process. That's just an exception. If it can have 8, it wants to have at least 8. If it has to be forced to have more than 8, then it has to be forced to have more than 8.
Okay.
The BF3, just look at that as an anomaly. Okay, Veronica?
Yeah.
All right. These are 3 different molecules, correct?
Yes.
Correct.
Which one's the right structure? Is one structure better than another?
No.
No? Remember, we looked and did formal charge of BF3, and we decided that that double bond with the fluorine wasn't very good structure, right? So we're going to do the same thing with each one of these. We're going to do formal charge. All right, guys, how many? You're going to do it for me. Actually, this is a good idea. Kara, Veronica, I want you to do the formal charge of the sulfur, carbon, and oxygen on the left molecule. Brian, Victoria, I want you to do the formal charge on the sulfur, carbon, and oxygen on the middle one. And who's left? Madison, Ramiro. Is that all that's here right now? Anybody whose name I did not call? I want you to do the formal charge on the sulfur, carbon, and oxygen on the right one. Okay? Do that. I will be right back. Still working.
Can you retype the formal charge equation on this
Oh, I'm
screen?
sorry. Yeah, I'm so sorry.
Thank you.
NVE stands for the normal valence electrons. LPE stands for the lone pair electrons. And BE stands for the bonding electrons. So you're going to look at the periodic table and determine the normal valence electrons. And you're going to subtract from that the lone pairs around that particular substance and the lone pairs around that substance and the bonding electrons divided by 2 added. Sorry about that. All right, the sulfur is in the center. Okay. Have you drawn the structure down? Have you drawn the structures down? Got everybody? You have these 3 structures down. Are you ready to give me your answers? Because if not, then I'm gonna go on. Keep on working. Keep on working. I've got something else I got to do. All right, this is 4 minus. Uh, 4 minus. Okay, what do we got? First,
16? 4, sorry, 4.
all right. Sulfur is 6 normal valence electrons minus 4 plus 4 over 2. Formal charge on the sulfur should be 0.
Oh, we're not doing the whole thing?
What whole thing, Veronica?
Isn't it like all of them together? Like when you,
No, you're doing each atom separately. Sulfur has 6 normal valence electrons. It has 4 lone pair electrons plus 4 over 2 bonding electrons. So you have 6 minus 4 plus 2. Sulfur's charge is 0. Oxygen, 6 normal electrons, 4 lone pairs plus 4 over 2. Its charge is 0. Who did it with you, Veronica? Who else? I'm sorry, who did the first compound? Is this the answer you came up with?
well, I thought it was all of them together, so I did not get that.
All right, is this the one, Veronica, I gave you?
Yes.
All right, who else besides Veronica had this compound?
Me,
Who's me? Madison?
Kara.
Kara?
Yeah.
Did you come up with 0, 0, 0?
I should have the carbon. I sure did, but for the sulfur and for the O, because I think it's just been a long day. It should have been 4 plus 4 over 2, but I did 4 plus 4 over 2. So that
Okay.
was,
So
I
you're
kinda
seeing
rushed
how
it,
it's
so-
0, 0, 0.
oh yeah,
Kara.
oh yeah.
Veronica, are you seeing how this is 0, 0, 0? Veronica, are you saying how this is 0, 0, 0, 0?
Yeah,
Sulfur, normal valence electrons are 6. There are 2 lone pair electrons around it. So this is 4. There are 4 bonding electrons, 4 over 2. 6 minus 4 plus 4 over 2. 6
Okay.
minus 6, it's
Yeah.
0. Same
I-
thing with the oxygen, 6 minus 4 plus 4 over 2, 6 minus 6, it's 0.
Yeah.
What did you guys come up with for the second compound?
I got it wrong, but
I got 1 for the S,
Plus
0,
1? 1
plus
plus?
1. Yeah,
Carbon,
0,
oxygen,
minus 1.
okay. I'm losing my electrons out here. But this oxygen, this one, 6 normal valence electrons minus, it has 2, 4, 6 lone pair electrons plus 2 over 2. That is a minus 1. The carbon, 4 minus no lone pairs plus 8 over 2. The carbon's going to be 0. The
wouldn't
sulfur,
for the oxygen, wouldn't it be 1 bonded?
I'm sorry, there should be,
There's 2 at the top.
these 2 count, these 2, and there were 2 that went away.
Wait, what's the difference between the LPE and the BE? I thought the
Lone
LPE,
pair electrons.
those are the dots, right?
Those are the dots around the terminal atoms.
And then the BE are the lines.
The BE are the bonding electrons. They're the lines.
Okay,
Okay, Brian?
yeah.
All right, what did we get for this third one?
-1, 0, +1.
I'll buy that. Now, if I was to tell you that the best structure is the one with the least amount of formal charge. 0, 0, 0 is the best option. Which is the best structure?
The first one.
First one is the best one. Now, if I was to tell you another rule on that is that the negative charge goes on the more electronegative element. Between this one, between the second and the third one, which one is more stable?
The last one?
What is more electronegative, sulfur or oxygen?
Oxygen?
Oxygen's more electronegative. Which one has the negative charge on it?
Oxygen.
The second one?
The second one has the negative charge on the oxygen. So this one is more stable than this one is. Are you understanding how this is working? Now, these are only 3 of my options. I got 6 more. Now, do you remember I said the least amount of formal charge, the better? Do you remember I said that? Now, if I put sulfur in the middle, look how that jumps up the formal charge. Okay, if I'm going to do the bottom one real quick, and I'm hoping I'm not making mistakes, that's 4 minus, this would be 2 plus. That is 2 minus, and that is 0. This one is 4 minus 2 plus 1 minus. That's going to be 2 minus, and that's going to be 3 plus. Is that right? 4 minus 2 plus 3. That's a negative 1. 6 minus, that's a 2 plus. And this is going to be a 1 minus. 4 minus 6 plus 1. This is going to be a 2 plus. And this. And this is going to be a 1 plus. All right, do you remember that rule I said at the very beginning? That you put the least electronegative one in the center. Look at all the formal charge that's going on when I didn't put the least electronegative in there. But when I put the least electronegative in, I have the least amount of formal charge. That's the reason that you do that. Bottom line. Bottom line, you do the formal charge to figure out what your most stable Lewis dot structure is. You make that determination, least amount of formal charge. Your second criteria is if you have a negative charge, it goes on the more electronegative atom. Are we good with this, guys? Madison's just about ready to bail on me because she's so bored. Are you okay, Madison?
Yes, I get it. I kind of did the lab already.
Sorry.
No, it's okay.
Victoria, Brian, Ramiro, are you kind of understanding what's going on here? We good?
Yes.
Yep.
All right. Second half of this is something called valence shell electron pair repulsion. Brian, do you have a brother?
No.
Sister?
Yes.
All right. When you guys got packed in the car, you got shoved in the back seat together, right, Brian?
Yeah.
All right. Now, were you right next to each other in the back seat, or were you as far apart from each other as possible?
Far apart as possible.
Same thing with atoms. atoms want to get as far away from each other as possible because they have electron density around them. If they have electron density around them, then they are repelling themselves from every other atom. Does that make sense?
Yeah.
They're also repelling themselves from every lone pair that's out there. So I got to get a little bit of vocabulary down. And the first thing we need to determine is something called an electron cloud. An electron cloud is any lone pair or bonding electrons. Each lone pair counts as one electron cloud. Single, double, or triple bonds count as one electron cloud. If it's a single bond, that's one electron cloud. Double bond, one electron cloud. Triple bond, one electron cloud. The other thing we need to deal with are lone pairs. Lone pairs are those electrons that are exclusively owned by that atom. They are not involved in bonding. Bonding electrons, on the other hand, are shared between two atoms. Those are the electrons that are between the atoms. So we also need to talk about electron domain geometry and molecular geometry. When I speak about electron domain geometry, I am talking about the geometry around the center atom. We include lone pairs and atoms. When I'm talking about molecular geometry, all we're talking about are the atoms. I'm going to skip this. Electron cloud geometry, very, very easy. If I have two electron clouds on a center atom, the electron geometry is linear. 3 trigonal planar, 4 tetrahedron, 5 trigonal bipyramid, 6 octahedron. So if I'm dealing with the geometry, I'm talking about, first of all, I need to determine what the electron domain geometry is, or the electron cloud geometry, the electronic geometry. It is dictated by how many clouds are around the center atom. If I have 3 trigonal planar, 4 tetrahedron, 5, I get a shape that looks like 2 3-sided pyramids on top of each other, trigonal bipyramid. 6, something like an octahedral, which means I have 2 4-sided pyramids on top of each other. That is the furthest away I can get one cloud from another. Is this making sense?
When you mean farthest away, what? I don't understand.
Okay, Veronica. All right, are you seeing my arms out, right?
Yes.
If I have an atom on this arm and an atom on this arm, the atoms that they want to be as far apart from as possible, it's going to be 180 degrees. Does that make sense?
Yes.
If I had them at 90, this isn't as far away from each other as they can go, right?
Yeah.
It has to be 180.
180. Yeah.
All right, if I have this atom here, the center atom, and the other atom here, and I shove another atom in there, well, this one pushes these 2 away, and it keeps on pushing them until these 2 start to push against each other. so that if all three atoms are the same, the bond angle I get from all three of these is 120 degrees. It's like I'm putting all three of these atoms at points of a triangle.
Okay.
So it is trigonal planar. Now, I shove another atom in there. That shoves all three of these down. One stays, one approaches it. It pushes all three of the other ones down until they start pushing against each other and they won't move down anymore. The shape that's formed when I have four things around there is a tetrahedron. I shove another one in there. What happens is I get two that are linear from one another and the other three that are on the plane in the center in which they have a triangle.
Yeah, I see now.
And the last one, I shove another one in there and it makes everything equally apart. And that is a 90-degree bond angle. The funky thing about the trigonal bipyramid is the ones that are on the plane here are 120 degrees away from each other. From the plane to the linear ones are 90 away from each other. That's the best we can do. Now, electron pairs push bigger than electron bonding electrons. If I have a lone pair by itself, that has the full power of the electron. Whereas if I have it bonded to another atom, that's spending some time around around the atoms, it doesn't have the full potential. So if I have a lone pair up here, that pushes down to a greater extent. The other thing about having a lone pair is I can't see electrons. All I can see are the atoms. And if I replace one of these atoms by a lone pair, all I can see is the white ball to the blue ball to the white ball. Something that looks like a bent geometry. If I have a tetrahedron and I have one of the atoms removed so that I have a lone pair, what I have down here is I have like a three-faced pyramid or a trigonal pyramid. A pyramid with three legs on it. If I take another one away, I have two lone pairs. Again, I have a bent molecule. Now, when I have five things around the center atom, and I take one of the atoms away and replace it by a lone pair, what you get is something that's like a seesaw shape. And basically, if you can think about it, if these are the two seats in the seesaw, you can think it goes up and down. If I have two things removed from a trigonal bipyramid, and I have two lone pairs, I get something that looks like it's T-shaped. Three things away, I have a linear molecule.
When we put the dots, is it because, what's the reason?
The reason is you have a lone pair.
Lone pair.
A lone pair there, a lone pair is occupying one of the electronic positions. Because it's a lone pair, Veronica, you can't see electrons. You can only see atoms. So that dictates that the shape changes a little bit.
Okay.
If I have octahedron, and I remove one of the atoms and replace it with a lone pair, I have a four-sided pyramid or a square pyramid. I take two of the atoms away. I now have four atoms that are on a square equally apart. That means that they are square planar. This is a very good slide. I stole it from a former text we used to use. Understand this. If I have determined, all right, 1 second, let me go to another slide, back up. The number of electron clouds on the center atom dictates the electronic geometry. If I have two clouds around that center atom, the electronic geometry is linear. 3, trigonal planar. 4, tetrahedron. 5, trigonal bipyramid. 6, octahedron. That's what it is. It has to be that way. Now, if I have 3 electron clouds and they're all atoms, the electronic geometry is the same as the molecular geometry. It's going to be trigonal planar. As long as I have no lone pairs, electronic geometry, molecular geometry are the same. If I have a trigonal planar, one lone pair, bent. 4 things. If I have a tetrahedron, if all 4 of these sites are occupied by atoms, my molecular geometry is also tetrahedron. 1 lone pair, I get a trigonal pyramid. 2 lone pairs, I have a bent molecule. If I get 5 things around the center atom, my electronic geometry is trigonal bipyramid. If all of them are occupied by atoms, my molecular geometry is trigonal bipyramid. If I have 1 lone pair, I have a seesaw shape. 2 lone pairs, T-shaped. 3 lone pairs, linear. If I have 6 things around my center atom, it's octahedral. No lone pairs. The molecular shape is also octahedral. If I have 1 lone pair, I have a shape that is square pyramidal. 2 lone pairs, square planar. If you're having trouble spatially trying to figure out what's happening here, you could spend $350 to $500 on molecular orbital kits. And if you're going to take organic chemistry, you'll use it then as well. I would suggest buying yourself a bag of pretzel sticks and a bag of marshmallows. $5, you can do the same thing. And when you get done at the end of the evening, you can eat the profits. So when you're determining geometry, draw the Lewis structure first. Count the electron clouds on the center atom. That will determine your electronic geometry. Then you apply, you kind of subtract, you kind of erase out the lone pairs. And that will dictate what your molecular geometry is. Okay, has anybody undergone hybridization yet? No? I'm getting a shaking of the head, no?
I have.
All right, God bless you. What you're going to have to do, the rest of you, you're going to have to just memorize this. What you do in hybridization, the reason this theory came about. Can anybody tell me p orbitals. What's the bond angle between p orbitals? You have an x, a y, and a z. What's the bond angle? What's the bond angle?
120?
X, Y, and Z. Cartesian plane. What's the bond angle between the X, Y, and Z plane?
90 degrees.
X, 90 degrees, right? We just got done telling you that the bond angles weren't 90 degrees, right? So they developed a new theory. And the theory they developed is that, well, maybe what's happening is we are hybridizing the orbitals. So I'm going to take an atomic orbital, an atomic S, and I'm going to put it with an atomic P, and I'm going to make a new orbital that I'm going to call SP. So if I have the need to have two things around my center atom, my hybridization is going to need two atomic orbitals, and that is going to be SP. If I have 3 electron clouds, I'm going to need 3 atomic orbitals to be hybridized, so I'm going to need an S and 2 Ps. That hybridization is SP2. Somebody had a question.
Yeah, so the 2sp will be the same as the linear, or is something different?
Yes,
Okay.
SP. Coincidentally, if I have 3 electron clouds around there, this is going to be trigonal planar. I have the need to have 4 things around my center atom. My hybridization is going to be 1 S and 3 Ps. A tetrahedron. 5 things I'm going to employ. Remember, I said that we grab d orbitals. So if I have 5 things, I have my S, my 3 Ps, I've run out of S and P orbitals. I have to grab a D. So I have sp3d, and this makes it trigonal bipyramid. Octahedron, 6 things around there. I need 6 atomic orbitals, sp3d2. So this is going to be octahedron. By the way, when you're doing this, if you see something like tetrahedral versus tetrahedron, the only difference between the two, tetrahedral is an adjective, tetrahedron is a noun. Only difference between the two. All right. One more thing. I have to talk about polarity. Now, when I'm dealing with polarity, it's a property of a covalent molecule, which orients the movement of the molecule when it's placed in a magnetic field. In other words, the molecule has unequal charges. That will make the positive end of the molecule gravitate towards the negative end if it's placed in a magnetic field. In other words, the molecule has a positive end and a negative end. It's the property that dictates solubility. Polar molecules dissolve polar compounds and ionic compounds. because polar compounds have charges, ionic compounds have charges, and so do polar molecules. Nonpolar do not have charges. They dissolve nonpolar. They do not dissolve polar. Like dissolves like. So basically, you have to deal with bond polarity. First off, electrons are not shared equally. If I have a bully like oxygen that is very electronegative, and I have a hydrogen, well, this is the worst case scenario, guys. This is like having, you're a 75-pound freshman, okay? And there is this 110-pound freshman that wants to beat you up for some unknown reason that I didn't mean to step on his lunch. So this kid is going to beat the snot out of you because he's big enough to do it. Yet he's not going to get in trouble for it. And literally speaking, he's not going to beat you to the point where you're in the hospital. He's just going to beat you up a little. I have oxygen, which is highly electronegative, and I have hydrogen. Oxygen is not big enough a bully to fully take the electrons away from hydrogen. But he is able to take them away for the majority part of the time. So if I have an oxygen and a hydrogen next to one another, that means that the electron spends more time on the oxygen. So in that entire bond, the oxygen end is going to be negatively charged. Hydrogen end is going to be positively charged. Is this kind of making sense, guys? All right. Now, in order to have a polar molecule, you need to have polar bonds. Polar bonds occur when you have a difference in electronegativities. But it needs something else. Sorry. All right, in medieval times, they had this quaint little custom called drawing and quartering. What they would do is they would tie each of your limbs to a separate horse and yell, "Giddy up." Your limbs went away, but your torso basically stayed the same because the horses were pulling in equal and opposite directions. If you have a tug of war between two 150-pound men, the rope is not going to move because they're pulling equally and opposite. So if I have a molecule like carbon dioxide, I have a polar bond. Oxygen is more electronegative than carbon. This oxygen is more electronegative than the carbon. So I get a negative end and I get a negative end, pulling equally and oppositely apart from one another. I have a totally balanced molecule. So if you think about the top end of this slide being the negative end of a magnet and the bottom being the positive, when this end starts to get attracted to the positive end, this one is getting repelled by the negative end. So this doesn't move in a magnetic field. It's not polar. It has polar bonds, but it is not polar. If I have a tetrahedron, you got to think in terms of physical vectors. This one, the top one, is pulling straight up. But these bottom are pulling to the left and right, and they're also pulling down. They compensate the left and right by canceling out each and every one of them. But as we're going down, this is pulling it down, but it's also pulling it straight up. This is a completely symmetrical molecule. So if each one of these sites were occupied by chlorines and the center was occupied by a carbon, I would have polar bonds, but each and every one would cancel because the molecule is completely symmetrical. If all of the atoms, if all the atoms around any one of these shapes, if all the atoms are the same, we have a completely symmetrical molecule. Even though the bonds may be polar, it's going to make a non-polar molecule. But change it. Change one thing on it. My tetrahedron here. Okay. If all four of these are chlorines, I have a non-polar molecule. Replace one of them with a hydrogen. I've made the molecule asymmetrical. Therefore, since it's asymmetrical, it is now polar. Questions, guys?
No.
No, totally bored. I know that Victoria is probably into, what are you into now? About maybe problem 10, Victoria?
No,
Madison's completely bored. She's already done. She has nothing to do because she's already done the homework assignment, right, Madison?
Yeah, pretty much.
All right. Let's go into the site itself, all right? Madison, did you have a hard time understanding the instructions?
No, one part that I had problems with, which I needed help with, is what the general molecular formula.
That, I'll
Like you have
s-
to put it in terms of A, X, and E.
Oh, that crap, yeah.
Yeah.
Yeah, I understand, totally understand. And that's a Dr. Musgrave thing. All right. Where is the thing? Oh, there it is. Okay. You have Madison. How long did it take you to do it?
Just the table, honestly, maybe an hour and a half.
And then the actual quizzes?
Oh, I haven't done those yet. I was waiting for you to go.
Ah. All right. Okay, guys, be prepared. Be prepared on this. You are going to have a compound listed. You need to draw the Lewis dot structure of the compound that's listed. And you have to read the questions. Read questions carefully when you are dealing with VSEPR or Lewis dots. It specifically asks you, how many lone pair non-bonding electrons does the compound possess on all atoms? Sometimes what they will ask you is how many lone pairs on the center atom. Be careful to answer the question that it asks. So first thing, draw the Lewis dot structure. Second thing, first question, you're going to look and you're going to count all the lone pair electrons, all the pairs of electrons that are not involved in bonding. The other thing you need to read carefully about the questions. Does it ask how many lone pairs or does it ask how many lone pair electrons? This is asking lone pairs. So you are going to count pairs of electrons, not individual electrons. First question, how many lone pairs? Second question, Okay. Second question, you're going to have to do 4 things. You're going to be answering 4 questions. The first question, how many electron groups on the center atom? Those are the electron clouds I was talking about. How many electron clouds are on the center atom? First question. Second question, number of atoms bonded to the center atom. Third question, number of non-bonding electron pairs attached to the center atom. Fourth question, it says general formula. All right. If it is an atom attached to the center atom, designate it by X and determine how many of that type of atom is around the center atom. If it's a lone pair, designate it by an E. If there are different atoms, go, say you have 2 chlorines and 2 iodines around a carbon. That would be designated as AX2, Y2. Let me see if I can give you an example. No, I don't want to mess that up. Oh, crap. I hope you guys appreciate the fact I'm wasting a whole new piece of paper on you.
I appreciate.
Okay, do you see this? Do you see the entire molecule? Do I need to move it back, left, or right?
Back it up some. Go up a little bit. Perfect.
All right, this is the structure for water. Okay, looking at this answer, electron groups around the center atom. 1, 2, 3, 4. So that answer, the first answer would be 4. Number of atoms bonded to the center atom. 1, 2. Number of non-bonding electron pairs attached to the center atom. 1, 2. General formula. Center atom is designated as A. Both of these are the same type of atom. So that would be AX2. I got 2 lone pairs, AX2, E2. This is really engaging, Ramiro, I can tell. Right, Ramiro? All right, let me get you another one.
Can I offer an example?
Go for it.
C2H2.
All right, I have to, if I do C2H2,
Yes.
I can do that. Simply looks like that. Are you seeing it, Madison?
Okay, yeah, that's what I did.
Okay, now you cannot answer the question because you don't know whether you're talking about that as your center atom or that. You have 2 center atoms there. You have to designate. The person asking the question has to designate. Are we talking about the left one or the right one? The answer for the left and right here is the same, but oh, that would work. Okay, do you see this molecule? Do you see this one? Sorry, need to finish it off. Are you seeing this molecule right here? I've got a carbon.
Up a little bit.
I'm sorry?
Can you go up a little? Yeah. Yeah,
I've got a
perfect.
carbon, 3 hydrogens over here, another carbon with a double bonded oxygen. Okay? Are we seeing this?
Yes.
If I ask you, what is the geometry about this molecule? I could not answer that because the geometry here is different from the geometry here. This has 4 clouds around it. This one is tetrahedron. This one has 1, 2, 3 clouds around it. This one is trigonal planar. Does that make sense to you guys? Bottom line, if you get 2 center atoms, you have to know which one you are dealing with in order to answer the question, what is the molecule? Does that make sense to you guys?
Yes.
Do we understand the second question? First point, how many electron clouds are around the center atom? And what Dr. Musgrave does is he will tell you specifically which atom he wants you to answer the questions for. Second question, the number of atoms bonded to that center atom. Third question, the number of non-bonding electron pairs. Then we get the funky formula. X's designate atoms, E's designate lone pair electrons. That's a wry smile, Madison.
So
Right.
is the number of electron pairs just the amount of things coming off the center atom?
Okay. Where's my water? Basically, unless you're told differently, the number of electron pairs, he's talking about the lone pairs on the center atom. Okay, Madison?
Okay.
All right, your third question. What is the overall electron geometry? Remember, count the clouds around the center atom. This has 1, 2, 3, 4 clouds. Overall electron geometry, tetrahedron. Then he asks for the hybrid orbital. I've got 4 electron clouds. It needs to be accommodated by 4 hybrid orbitals. And it goes in order. S, P1, SP2, SP3, then SP3D, SP3D2. Questions about this portion? Fourth, what is the molecular shape? Okay, molecular shape. Electronic shape, 4 things around it is tetrahedron. Molecular shape, I can only see the hydrogen, the oxygen, and the other hydrogen. Bent.
These questions are just for the water?
Just the first 5 are the water.
Oh, okay.
Second, last question. Is the molecule polar? Is there an electron? Is there electronegativity difference between oxygen and hydrogen?
Yes.
Is it a symmetrical molecule?
Yeah.
Is this symmetrical? Is the top half the same as the bottom half, Veronica?
No.
Yes.
No. This oxygen doesn't have a hydrogen up here, does it?
Oh, okay, no.
It's not the same top to bottom. So it's asymmetrical. If it's asymmetrical and it has polar bonds, your molecule will be polar. 5 questions. Then you have methane. 5 questions. Then you have hydronium ion. 5 questions. Are we sensing a pattern here, guys? NH3, 5 questions. C2H4. First question, how many lone pairs does the entire molecule? C2H4. This has two center atoms.
I wanted to ask you, you said the difference of, can you go up in the first question for that one? The difference between the lone pairs and the lone pairs electrons?
Lone pairs are pairs of electrons. Lone pair electrons, you count the individual electrons.
What he's saying is if it asks you like how many lone pairs, so if you had 4 dots, that would be 2 pairs.
This
But
is
then
a
if it
bad
asks-
example. This is a particular bad example because this is, do you see the drawing?
Yeah.
There are no lone pairs. So it's a bad example. Now, Madison, I'm sorry I interrupted you.
No, just explaining to her that what he was saying is that if it says how many lone pairs, so if you had 4 dots, that would be 2 pairs. But if it says how many lone pair electrons, it would be 4 because it's 4 dots.
Oh,
That makes
okay.
sense.
Yeah.
Okay, we good with that?
Yes. Thanks.
Okay. This one, C2H4. Just choose one of the carbons. Both of the carbons are the same. Just choose one of the carbons. Because he doesn't give you an A2. So just choose for this one of the carbons, which is going to basically be AX3. Because where did it go? There it is. When you have this molecule, it has 1, 2, 3 atoms around it, no lone pairs. So answer it according to either this one or this one. They are both the same. In any case, you're going to have the same questions over and over again for all these different compounds. Yes, it is almost as bad as the nomenclature. And right now we're into 83, 84 questions. Ninety total questions, guys. Don't shake your head at me, Kara.
Too late.
I'm sorry. I apologize for that. He likes repetition. Post lab.
Just quick question before I forget. So what was the A for and the
A
X?
is the center atom. It's the center atom that's associated with that.
And the E is the lone
The
pairs.
number of lone pair electrons on the center atom. So if I was dealing with water, A is going to be what the oxygen is. It has two of the same atoms, so that's AX2. It also has two lone pairs. So that is AX2E2.
What the X means?
Atoms. X is atoms attached to the center atom. E is lone pairs attached to the center atom.
Okay.
Now you understand what I meant by telling you that I really wanted to take you through this, guys. Okay, preview for the post lab. And I hope he doesn't have 20 million questions. I don't really remember what this is about. Okay, apparently it's more of the same. NH2Cl, figure out how many valence electrons there are. How many lone pairs are around it. How many bonds there are there. Shape the atoms make. This is what I've been referring to as the molecular shape. Is the molecule polar? Thank God he didn't go crazy on that. 5 questions for the post lab. Anything else, ladies and gentlemen?
I got a question.
I'm here.
Okay, I want to make sure I got this right. So for the same C2H2 example, how many atoms are bonded to the center atom? Like, do you?
2.
So the two, one of them is hydrogen and one of them is carbon.
Yes.
Like, you don't count the number of bonds. It's just the literal.
Correct.
Okay, got it.
Correct.
Thank you.
Correct.
Thank you.
That's like it's like when I was saying electron clouds. This triple bond counts 1 electron cloud. This single bond counts 1 electron cloud. So this carbon has 2 around it.
Okay, I got it now. Thank you.
All right.
So it means the other side has 3? Because you have like a C on the top.
Where?
Am I going crazy? Maybe I'm just going crazy.
You're going crazy. It's not there.
Okay.
What else can I help you with, guys? Do you have a rudimentary understanding of Lewis dots and VSEPR? Are we good
Yes.
with that? Ultimately, it's not that hard. If you follow the rules for Lewis dots, you can make a good Lewis dot structure. And if you make a good Lewis dot structure, all you got to do is count the things around the center atom. That gives you the electronic shape. Then kind of mentally subtract out the lone pairs. That will give you the molecular shape. Something I do want to check to make sure it is in there. If it's not, I will put it in right away. Okay. All right, I'm just putting in the PowerPoints, if you find those to be of value. This is 2 of the PowerPoints I used tonight. I don't know where the third one is. I could probably find it. Now, I don't know where it's at right off the top of my head, guys. Those should help you anyway. Anything else? Anything else I can help you with?
No, I think that's it. That's all we have to do, right? That will be the last lab.
Isn't that enough?
Yeah, it's enough. 90 questions, and I think it's enough.
Yes. Veronica, you actually made a good point. Ladies and gentlemen, it's been my honor this semester to teach you guys. It really has. You guys have been spot on. You've been attentive. You have been everything I could have wanted from a class. You're dynamite. Keep up your curiosity, ladies and gentlemen.
Thanks. You were a great professor too. You make
Thank you,
us
Veronica.
make a good.
Uh-oh. The TV stopped?